This table shows how often each binge level happened in the class. Most students stuck to 1 to 2 episodes, which is healthy-ish. A few watched 0, either disciplined or still crying from the last cliffhanger. And then there's the one hero who watched 8 episodes straight, proof that next episode is the most dangerous button in human history. Ungrouped distributions are like exposing your YouTube stats without filters. You see every awkward detail. 3 shorts barely crawling to 1 like, 6 that managed 2 likes thanks to my mom's multiple accounts, and 1 glorious video that hit 7 likes. Basically viral, right? I'd better quit my influencer dreams and stick with my college professor job. This table shows student heights grouped into intervals. Most of the class huddles in the 170 to 179 range, which basically means close to average heights are the most frequent. This is true for organic measurements including heights, weights, head circumference, enzyme levels, and reaction times. There's one lonely student in the 200-plus bin. That's not just tall, that's watch out for the ceiling fan tall. Statisticians call these exceptional individuals outliers. When creating a grouped frequency table, the art is in balancing simplicity and detail. Too few classes hide patterns, too many just bury you in noise. Pick a sensible starting point, calculate a width that covers the range, and keep the classes consistent. Think of it like slicing a pizza. You want enough slices to share, but not so many that each slice is thinner than your GPA after finals. With 40 values, Sturge's rule points to about 6 classes, which balances detail and simplicity. The range is 51, so dividing by 6 gives about 8.5. We round to a width of 10 for cleaner intervals. Starting the first class at 150 instead of 153 makes all classes neat decades. 150 to 159, 160 to 169, etc. Class boundaries are found by subtracting 0.5 from the lower limit and adding 0.5 to the upper limit. This avoids gaps between classes. For example, 150 to 159 becomes 149.5 to 159.5, and the next one 160 to 169 starts exactly at 159.5. That way the intervals connect smoothly like Lego bricks. Class marks are just the midpoints. Add the lower and upper limit, then divide by 2. So for 150 to 159, we get open parenthesis 150 plus 159 close parenthesis divided by 2 is equal to 154.5. These marks are handy when drawing histograms, polygons, or doing calculations, because they give one representative value for the whole class. This way, the table is not only accurate but easy to read, plot, and explain. It's like cleaning your room. You don't just shove things under the bed, you make the bins line up nicely. We started with 50 raw newborn weights between 2.5 and 4.4 kilograms. Using Sturge's rule, K is approximately 7, which balances detail and simplicity. The range is 1.9, so dividing by 7 gives a width of about 0.3 kilograms. Starting at 2.5 and stepping by 0.3, we cover the full range neatly. To get the boundaries, subtract 0.05 from the lower limits and add 0.05 to the upper limits. The table shows most babies weigh between 3.4 and 3.9 kilograms, with very few at the low and high ends. Exactly the insight we want from grouping. A histogram is useful because it gives us a quick visual summary of how data is distributed across intervals. Instead of staring at a long list of numbers, we can instantly see where most of the data clusters, whether the distribution is symmetric or skewed, and if there are any unusual gaps or outliers. It basically turns raw data chaos into a picture that our brains can understand in a split second. Relative frequency is useful because it puts frequencies into perspective. Instead of just saying 7 students are in this height range, we can say that's 17.5% of the class, which is way easier to compare across groups of different sizes. Cumulative frequency is handy when you want to know how many observations fall below a certain value, like counting how many students are shorter than 180 centimeters. Relative cumulative frequency takes it one step further by showing proportions, so you can say things like 70% of the class is below 180 centimeters. Together, these measures turn raw counts into insights about proportions, comparisons, and thresholds, the kind of stuff you need when you want to sound smart in a business meeting. A relative frequency histogram is useful because it puts the data in percentages, making it easy to compare samples of different sizes. Imagine you need to create 2 histograms, one for boys and one for girls for comparison. If the number of boys in your sample is not the same as girls, then 2 relative frequency histogram with identical class limits makes the most sense. Here, instead of just saying 16 students are between 170 and 179 centimeters, we can say 40% of the class is in that range. Talking in percentages rather than in raw head count is way clearer, and it saves you from hearing, but how many students were there in total? A frequency polygon is useful because it shows the overall shape of the distribution more clearly than a histogram. By connecting class marks with straight lines, we can quickly see peaks, symmetry, or skewness, and it's easier to compare multiple data sets on the same graph. In short, the polygon gives us the outline of the data's mountain range, so we can study its shape without all the extra clutter. A cumulative frequency polygon, or ogive, is useful for showing how the data accumulate across class boundaries. It makes it easy to answer questions like, how many students are shorter than 180 centimeters? Because you just read the cumulative count at that point. A relative cumulative frequency polygon is useful because it shows the proportion of data values below a certain point. That means we can read medians, quartiles, and percentiles directly from the graph. For example, the median is where the polygon crosses 0.5 on the vertical axis, so 174.5. Can you approximate the 60th percentile from this graph? You should get 177. Legend has it that Sir Reginald Percentilus first invented the ogive while keeping track of how many mugs of wine were consumed before the inevitable bar fight began. The rising curve gave him uncanny power. By the 10th mug, he could predict with frightening accuracy who would be singing, who would be sleeping, and who would be swinging fists. Historians still debate whether this was statistics or sorcery.